Hello guys, welcome. Today we'll see the part 2 of data encryption standards where we'll be talking about the analysis, the weakness and the cryptanalysis on DES. So in the previous lecture we had talked about the initial and the final permutations and the rounds, the number of rounds that DES has, and scientists say that 16 rounds are the minimum requirement in order to create a good confusion and diffusion. And we also talked about the heart function, that is the DES function as well. That is a combination of the various compression or expansion, straight permutation boxes and the substitution boxes and XORing components, right? So having gone through all that, today we'll be talking about the analysis part. The first one is your avalanche effect, and we'll see that how good does DS perform in the avalanche effect. And avalanche says that if you are changing the plain text even by a single bit, there should be a significant change in the ciphertext. And once you have created a DES, data encryption standard, and you provide an input of the kind like, and the ciphertext that you get, if it is, and if you change the plain text second time by just one bit, then the ciphertext correspondence is absolutely random that you will be getting. So the relationship between the small change in the plain text, that is creating a significant change in the ciphertext, and therefore we see that the DES performs very good with respect to the avalanche effect. Secondly, it says about the completeness effect, and the completeness effect means that each bit of the ciphertext should heavily depend on the plaintext bits. And if you remember, when we talked about the confusion and diffusion in previous lecture, there we had drawn a diagram where we said that one bit change in the plain text is, with the help of the substitution boxes, getting reflected into 2 bits, and then with respect to every round it is increasing by an order of 2, right? So one change in the plain text is causing significant change in the ciphertext as well. That means that one bit is having an impact on many bits of the ciphertext. So each bit of the ciphertext should heavily depend on the plain text, is what is very thoroughly achieved in the DES with the help of the confusion and diffusions through permutation and substitution boxes. So it has the completeness effect as well. The weakness in the DES is, as we had discussed in the previous lecture, that in permutation boxes we said the initial and the final permutation boxes, we don't know the exact security usage that it has, so that is termed as one of the weaknesses. And then the mapping of the permutation boxes are also fixed. Then in substitution boxes, people say that there are certain substitution boxes like S4 where you can deliberately give it an input and get the expected output, but there is no public acknowledgement of the compromise of the S boxes so far, and therefore we cannot exactly comment that the S boxes have got the fatal weakness in them. Therefore we'll be talking about the weakness with respect to the keys. If you are using a key of the kind like 0 or 0 and a sequence of F's, this is the hexadecimal representation, because 56 बिट्स में हम ऑपरेट करते हैं फॉर कीज, तो उतने बिट्स लिखने के बजाय हेक्साडेसिमल रिप्रेजेंटेशन यहाँ पे दिखाया गया है. इफ यू आर यूजिंग any of these 4 keys that are mentioned over here and you apply DES twice, then these weak keys will generate the plaintext back. That means once you have applied the DES, you get a ciphertext. If you are using this weak key as the key for the DES, then if any person gets that ciphertext, the middle text, and performs the DES with the same weak keys, and then he will get the plaintext back. So he doesn't have to perform a significant operation in order to break the DES. Therefore, weak keys should not be used. But you will see that these weak keys are very less in number. There are certain semi-weak keys as well, and these semi-weak keys again have got this property that they get the plaintext back, but not necessarily just after one round. They may get it after a few rounds. But it's easy to get the plaintext back with these weak keys, so we need to avoid them. If we talk about the overall key domain, it is humongous, and the weak keys are very limited, right? So this is one of the weaknesses of the keys, but they are very limited and you must not use such kind of keys. That's it. If you want to perform a brute force in the DES, and we have said that DES after the parity drop in the key generator will have 56 bits of key domain, and that 56 divided into 28 and 28 bits which is provided in the circular shifts, which generates the corresponding keys for every round, right? Now the attack that has to be performed in order to generate those keys is on the 56 domain, and brute force says that if we search half of the domain, then the remaining half may not be searched and we'll be able to find the key. So 2 raised to the 55 possible keys could be generated, and that has to be checked in the brute force. It appears to be a very large number, because if you are generating 10 to the power 6 keys per second, then also it would take about 2000 years to do the brute force attack, which is quite impractical. And one more thing, that why do we use 2 raised to the power 55 keys is that if I'm calculating the ciphertext, the formula is encryption with the key and P. The complement of the ciphertext, since these are in bits, that the complement means that 1 is converted to 0 and 0 is converted back to 1. So the complement of ciphertext is equals to the encryption of the complement of key and the complement of P. Therefore, if you are performing the brute force on half of the domain, the remaining half can be calculated automatically. Therefore, this is 2 raised to the power 55 keys. Alright. In 1998, a special computer with the purpose of breaking the DS was created, and that special computer took about 12 hours to break the DS. So this pretty much tells us that if you make a deliberate attempt in breaking the DS, the 56 bits key domain is not very large and it can be broken down. Even in 1977, RSA lab used 3500 network computers to compute the key in 120 days. So that means DES is susceptible to brute force attack, and 56 bits key domain is not very large. So D is not very safe with respect to the computing power that we have today. Therefore, multiple DS concept came into existence. Now, this multiple DS means that you are using DES multiple times. So every DS has got multiple rounds, and multiple DS ciphers have been implemented in order to create the ciphertext attack. So if you are using the DS 2 times, then you are getting a ciphertext. So when you are calculating the inverse of the DS, you will find that, so this is DS inverse, basically the reverse cipher. Reverse cipher will have 2 keys. 2 keys means that you have got 56 bit keys over here and the 56 bit keys over here. So presumably it appears that the key domain that we have here is 56 plus 56, that is 112 keys. Therefore, it appears that it should be 2 raised to the power 111 keys that have to be generated for the brute force. But we can perform a man in the middle attack. So man in the middle attack would like to attack on this middle text. So this middle text is generated with the help of 2 raised to the power 56 keys. So the brute force would require 2 raised to the power 55 key domain in order to calculate the key, right? And now you have got the middle text, that is M. From if you have got the ciphertext, and on that ciphertext you again perform a man in the middle attack. So again you will be going through the 56 bit keys, generating 2 raised to the power 55 keys, right? So now you will get the M again. If these two M matches, so that means you have compromised K1 and K2 both. And how many computational keys have been generated over here? 2 raised to the power 55 over here and 2 raised to the power 55 over here. So that means twice of 2 raised to the power 55, which is equal to 2 raised to the power 56 keys. So it appears that my key domain is going to be 2 raised to the power 111 keys, but it is not so. It is just the double of the initial DES, and again this is not a very large number and can be broken down. In triple DES, we use either 2 keys or 3 keys. The version that I am showing over here is of 2 keys. When I am using 2 keys, the domain is 112 keys. So brute force would require 2 raised to the power 112 key generation, and here it is 168 keys. So it requires 2 raised to the power 168 keys to be generated, right? In 3 keys, you will be using a K3 key over here for this example I am talking about, right? you are not just using DES cipher, but you are using a DS cipher, then the inverse of the DS, and again a DS cipher to calculate the ciphertext attack. Here you cannot perform the man in the middle attack, and even if you are performing a man in the middle attack, you will at this point or at this point, you will find that in order to generate this value, you have to go through two ciphers. In order to generate this value, you have to go through two ciphers, right? So in both the ways, the key domain is getting larger as compared to the double DS, right? So triple DS is more resistant to brute force attack. So we have talked about the brute force in the cryptanalysis, and brute force is comparatively easy. So we go for multiple DS options, and triple DS with 3 keys is a good option for avoiding the brute force attack on the DES. And then we have got differential cryptanalysis and linear cryptanalysis. And differential cryptanalysis reduces the key domain to 2 raised to the power 47, and it is a chosen plaintext attacks proposed by Ali Beham and Eddie Shamir. And linear cryptanalysis further reduces it to 2 raised to the power 43 keys. It is a known plaintext attack proposed by Mitsuru Matsui in 1993. So you see that even after the application of differential and the linear cryptanalysis, the key domain is not reducing considerably. There is improvement by a factor of 2 raised to the power 12 over here, and by a factor of 2 raised to the power 8 over here, right? But it is again not a very significant improvement. Brute force can be performed, yes. Even after differential cryptanalysis, you can break it, but you need a brute force attack for compromising the system. But differential cryptanalysis in itself is not reducing the key domain to a great extent that you can easily break the DES. So it is somehow resistant to it, but again brute force could be performed with the specialized computers in order to break DES. So let's look into what differential cryptanalysis is. So the overall diagram, if I show you, the concept of the differential cryptanalysis is that your DS cipher has got several rounds, and every round has got a DS function that you perform, right? If I am representing all these rounds, there are 16 rounds, by a single large function, and I say that there is an input plain text and there is an output ciphertext, then it goes through the FRth round and gives again a ciphertext, right? So the differential cryptanalysis is a non-generic cryptanalysis that basically acts upon the design of the DES cipher, and based on the design it says that since I am using the XOR operation in my function calculations, so if I am choosing my plaintext in such a way that once I provide P1 and the next time I provide P2, then I study that what is the value of C1 and C2. Is there a relationship between these two? So one of the values is that my C1 is equals to P1 with respect to K key1, and C2 is equals to P2 XOR K2. If I find out the C1 XOR C2, it is equals to P1 XOR K1. I'm sorry, this is K1 over here. Why? Because we are passing the same values into the same function, right? So the key is going to be same, but ciphertext and the plaintext are different. XOR P2 XOR K1. So K1 and K1 XOR will be 0. So it's P1 XOR P2. What does C1 XOR C2 and P1 XOR P2 means? So P1 XOR P2, if I assume my P1 to be 0 0 1 1 and P2 to be 0 1 1 1. If I XOR both of them, I'll find that 1 1 is 0, 1 1 is 0, 0 1 is 1 and 0 0 is 0. So we'll see that P1 XOR P2 basically tells me where the bit is changing. If one of the bit is changing in P1 and P2, it will have 1 occurring at one place only. And the remaining bits, this one is same, this one is same, there is a difference, and then this one is same. So it has got zeros. So the number of ones in P1 XOR P2 will tell me how many bits have changed in the two plaintext. And similarly, the C1 XOR C2 tells me that how many bits have changed in the ciphertext. And we see that there is a relationship between C1 XOR C2 and P1 XOR P2 over here, right? and we would like to exploit this very relationship. So differential cryptanalysis says that if I am selecting my P1 and P2 in such a way that the difference between them is alpha, then the difference between C1 and C2 will always be beta with a very high probability. So it may change, sometimes it is beta, sometimes it may be gamma or some other function, but with very high probability we'll get the change as beta, right? If I'm true and my this particular probability equation holds, then if I'm performing an inverse cipher from the ciphertext that I have over here, then going back it will produce, suppose y1 and y2. After performing the inverse cipher, this y1 should be equal to c1 and this y2 should be equals to c2, or we can say that y1 XOR y2 should be equals to beta. So if this holds true, that means the key that I have supplied in the frth function, that is kr, then this key will be the key that we are looking for. So we'll make a table for the keys over here, and with respect to the kth key that I'm trying over here, I'll increment it by 1. So in this way, for different sets of ciphertext and the plain text, the kr that we are calculating, we will have like kr0, kr1 and many other keys that would be generated. The one with the highest frequency will be considered the key for the frth function, right? So this way we try to compromise the key. Now the possible combinations that we generate and the key that we are trying to find out is a 48-bit key over here. Therefore the key domain for this kind of an attack is 48 bits, and therefore it takes 2 raised to the power of 47 key domain to perform this particular attack. So let's see it through an example. So actual functions have got 32-bit and 48-bit operations, but we will talk about 3 bits and 2 bits for the simplicity. So I am taking my plain text to be 3 bits, S box is 3 cross 2 bits, and key is also 3 bits. So the relationship P1 XOR K is C1 and P2 XOR K is C2, and this I have shown that C1 XOR C2 is equals to P1 XOR P2. That means the change in the ciphertext and the plaintext have got a relationship in between, and this diagram represents the mapping of the S boxes, and you will see that these S boxes are 3 cross 2, so they are not invertible. Means that when you are looking at the ciphertext and if you want to get an exact value of x, you won't get it, because if the ciphertext is 0 0, then two values of x would be generated. So you are not one to one mapped, therefore these are not invertible, but we will try to exploit whatever relationship is there in the S boxes. So for a chosen plain text attack, you choose deliberate plain text P1 and P2, and then you calculate the XOR of P1 and P2. If you are having P1 and P2 in 3 bits, the possibility is that the two plain texts are same and therefore there is no difference. So XOR would be 0 0 0. Maybe the rightmost bit has changed, therefore the relationship would be 0 0 1. And maybe the middle bit has changed, maybe middle and the rightmost has changed. So there are 8 possible combinations for the plain text that you generate, and since the ciphertext is in 2 bits, therefore either there will be no change in the two ciphertext, either the right bit changes, left bit changes, or both the bits changes. So in this way you will be calculating that for a change when there is no change in the plain text, 8 of the 8 times there will be no change in the ciphertext as well. But if the rightmost bit of the plaintext is changing, you will see that sometimes you get two ciphertexts where there is no change at all. Sometimes the right bit changes and sometimes both the bits changes, right? So in this way, if you are fixing it to be the alpha for your particular example, that you are going with the relationship where P1 XOR P2 is equals to 0 0 1, then you will calculate that with what probability does the bits of the C2 changes. So when I convert it to the probability distribution, I'll find that 0.5 is the highest probability over here. So there is a good chance that your P1 XOR P2 maps to the C1 XOR C2. So this becomes beta for me. Alright. So this alpha and beta relationship exists. Once I have found this out, then we move on to the next function and we try to generate the plain text from the ciphertext, right? So the plain text from the ciphertext that we generate over here and the one that we get from here should be same, should be having the same beta values, and the beta values is that both the bits of the ciphertext should change. So when we perform a chosen ciphertext attack, we choose a ciphertext C1 and C2 and we get P1 is equals to 010 and P2 equals to 011. Now we will try to find out the K based on the S box details that we have over here. So if C1 is equals to 00, the possible values for X1 could be 0001 or 111. If X1 is equals to 001, relationship with which you have got the X over here is P XOR K gives you X. So the inverse process will give you the X XOR P equals to X. In order to calculate the K, the formula is X1 XOR P1. So if I am assuming my X1 to be 001 and P1 that I have got over here is 010, I will find that the K is 011. But if I am using my X1 to be 111, then the value of K comes out to be 101. And if I repeat this process again with C2, I will again find that the key values are 011 and 101. Now that means that there are various possible keys for this particular round. So I'll make a table of such keys and I'll increase the frequency of the occurrence of a particular sequence in the key. The key with the highest frequency will be selected as the key for that particular round. Alright. Other inference that I can make is, since the rightmost bit does not change in the key, so it is almost decided that the rightmost bit is going to be 1 in the key. That is one more inference that I am getting out of it. So this is your differential cryptanalysis that you basically perform on DES. DES is resistant to it because the domain of the key is not getting reduced significantly. Initially it was 2 raised to the power 55. After differential cryptanalysis it comes out to be 2 raised to the power 47. So there is a factor of 2 raised to the power 8 reduction in the key domain. In linear cryptanalysis, we again make a probabilistic arrangements and we try to find out the relationship in the S boxes, and if the relationship of the S boxes can be expressed in the equation of this order, then we can say that they are linearly related to each other and a linear cryptanalysis can be performed. So here the ciphertext C0, one bit C0 is dependent on the X0 and X1 bits from the 3-bit number that we have as input to the S boxes, and based on this data we can compute that X0 is equals to P0 XOR K0. So P0 XOR K0 is replaced over here and P1 XOR K1 is replaced over here. When we get these 3 equations, then from these 3 equations we can generate the values of key. For example, if I add C1 and C2, you will find that P1 XOR P1 will result in 0, K1 will result in 0, P2 will result in 0, K2 and K2 will result in 0. So C1 XOR C2 will be equals to P0 XOR K0. So for calculating K0, we'll add both the sides by P0. So it cancels out the P0 over here and the relationship comes out to be K0 equals to P0 XOR C1 XOR C2. Let me just show you how this has been calculated. So if I am performing C1 XOR C2, that means P0 XOR K0 XOR P1 XOR K1 XOR P2 XOR K2 XOR P1 XOR K1 XOR P2 XOR K2. So P2 results in 0, K2 results in 0, P1 XOR P1 results in 0, K1 XOR K1 results in 0. So now this is equals to P0 XOR K0. If I XOR both the values by P0, then this P0 becomes 0. Therefore, K0 is equals to P0 plus C1 XOR C2. So this is a relationship that we have got over here. So this way you can calculate the values of key in linear cryptanalysis. Thank you.